is Soviet and this is my 5-minute thesis. So a little bit of an introduction. Currently we are facing a lot of environmental issues in our world, and these environmental issues stem from an increase in greenhouse gases, predominantly CO2. So how do we fix this problem? Number one is through carbon sequestration. In layman terms, carbon sequestration is the process of collecting environmental CO2 and pumping it underground, as we can see here. So on top are the sources of the CO2, and at the bottom is where CO2 is being used. So CO2 is used in enhanced oil recovery through gas injection and also through CO2 storage. So this CO2 storage is carbon sequestration. Where can we store this CO2? Number one, depleted oil and gas reservoirs, deep saline aquifers, and also coal bed methane that cannot be mined. Which leads me to my topic. So my topic is regarding the effectiveness of carbon sequestration and also coal, which is the title, Effect of Brine Composition and pH on the Wettability of Coal. Now you may ask, why am I using coal? It's because of coal's wetting characteristics that make CO2 preferentially adsorbed to it, which means that coal is predominantly gas wet. So how am I going to measure this? It's through two methods, which is the contact angle method and also the zeta potential method. So for my first method, it is the contact angle method, where we'll be measuring the angle of which the droplet creates when it forms on the coal surface. So there are three different wettabilities when you measure the contact angle. From 0 to 75 degrees is water wet, from 75 to 105 it's intermediate wet, and from 105 to 180 it is gas wet. So this is how the droplets will look like when it is formed. So for water wet, the droplet is quite flat, which shows a high affinity to the surface. When it is intermediate wet, it will be a bit bigger. And the largest one form is when it's gas wet, between 105 and 180, it's a very big droplet. So, how am I measuring my values for this experiment? I'm using the IFT 700 equipment, which uses the Cecil drop method, where the droplet forms on the top, lands on the curved surface, and then you measure your angle from there. For the conditions, I'm using different salinity conditions of 0 ppm all the way to 30,000 ppm, different pH conditions from 5 to 9, which simulates an acidic environment, neutral and alkaline environment, a pressure of 10 and 15 megapascals, and a temperature of 305 Kelvin. These two is to simulate the reservoir conditions of supercritical CO2. So the second method is the zeta potential method. Now zeta potential is essentially the difference in potential between the particle and its ionic atmosphere surrounding medium. So as you can see here, this is the concept of how zeta potential works. This is a negatively charged particle, which is a result of when the particle dissolves into the medium. So what happens is it becomes a negatively charged particle, it attracts positively charged ions, which forms the stern layer. So up till here is the stern layer. But what usually happens for some particles is these positive ions do not fully balance out the surface charge, which then results in the attraction of other ions outside the stern layer, which forms the diffuse layer. So now the combination of the stern layer and diffuse layer forms the electric double layer, short form EDL. So what the purpose of the EDL, or the function of the EDL, is to aid in the stability of these particles in the medium. Because when the EDL is big enough or thick enough, it prevents the particle from coagulating with other particles due to like charges. So when two particles of like charges come to each other, they repel. So thus they don't combine and coagulate, which aids in the medium being stable. So there's no reaction going on. So as you can see, this at the very start is the surface potential. Then you have your stern potential, and then finally you have your zeta potential. So zeta potential is what we are trying to measure. Now you may ask, of all of this, how does it help in terms of wettability? So which leads me to the significance of zeta potential. Firstly, zeta potential influences the adsorption of ions and molecules from the liquid onto the solid surface, which in our case is the coal. Secondly, it determines the strength of electrostatic forces between the surface and the liquid, so between our coal and our brine. Thirdly, most importantly, it influences the contact angle formed between the liquid droplet and the solid surface. So in terms of relating both contact angle and zeta potential, a low zeta potential value will result in a high contact angle. What does this mean? It means that the surface is hydrophobic, which means it's water fearing. So in terms of when it's a high zeta potential value, it will have a low contact angle, which means it is hydrophilic, which means it's water loving. So the conclusion to my thesis is pretty simple. What I'm trying to find is more gas wet findings from my contact angle and zeta potential measurements. Why is so that it can indicate that more CO2 can be adsorbed onto the surface of the coal, which means that CO2 fills up the smaller pore spaces in the coal, which both of these result in more efficient CO2 sequestration. Thank you.